afternoon, good evening, everyone. Please, can you hear me? Okay, so welcome everyone to today's program or today's session. So we are excited to have you to join us. So we'll delve into quantum computing today, and person taking us is Lia from Quantinuum. So please join me in welcoming her, our speaker, and let's make the most out of today. And remember to raise your hand when you want to ask a question and mute your mic.
Hello, everyone. Thanks for joining today's lecture. And thanks, Henry, for the introduction. If you have any questions, feel free to ask via the Zoom raise hand function or the chat box, whichever you prefer. And please don't hesitate to ask at all. So, so 2 days ago, you guys got from Razine the previous week, but it was rescheduled to 2 days ago, about up to definitions of spiders and what spiders are in the ZX calculus. So this time we can continue off it. We'll get to see what each of the normal qubit quantum states and gates looks like, and measurements. So that's what I plan to cover today. So Razine said that he got up to covering single qubit states. So I'll start by reviewing that. So this one is ket 0. In fact, I'll just write it like. This is ket 0. Let's just go from bottom to top for today. We'll also go bottom to top and left to right. So for circuits are left to right, but bottom to top sometimes is easier to see, easier to read. So these red spiders, they're diagonal on the x basis, but these are z basis single qubit states. So these are eigenvectors of the z gate. So this is ket 0 and ket 1. And one kind of useful way to remember. So if you recall the definition, this one is equal to, the definition of x spider is equal to plus. Okay, maybe I'll just draw and then speak and then draw and speak. So this ket 0 up to a scalar is equal of 1 over square root of 2 is equal to ket plus e to the I alpha ket minus for the special case of alpha equals 0. So when alpha equals 0, e to the I alpha is e to the 0. And that's the same as just the number 1. So that's why ket 0 is up to this factor that let's ignore for now, is equal to ket plus ket minus. Yeah. I'll just put the factors here. Usually with ZX calculus, you don't have to keep track of it explicitly. If you're just checking, say, if quantum circuits are equal, or if you're working with some quantum protocols or algorithms where you know the probabilities will be normalized. But some cases, for example, you're calculating the amplitude of certain probabilities, then you do want to have the correct scalar factors. And also, I'll do the same for ket 1. And now alpha is pi. So e to the I pi is just -1. So it's just equal to square root of 2 times ket 1 is equal to ket plus minus ket minus. Then we can do the same on the other two. And so this is the review of all the single qubit states and why the 0 input, 1 output case of these green and red spiders with 0 or pi phases is exactly your z basis and x basis states. So what Rosine also showed you last week is the copy rule. So this 1 input, 2 output green is such that if you plug in a computational basis state here, either ket 0 or ket 1, because A is either 0 or 1, then you exactly get 2 copies of that same computational basis state. This is perfectly well defined in quantum computing and quantum information because although you have the no cloning theorem for quantum mechanics, but you can still copy quantum information if you know which basis it is in. So if the state that you're trying to copy is within the basis that copy operation is defined on. So in this case, this is diagonal and copying anything in the z basis, and these are z basis states, so it's okay. Likewise, it goes the other, if you flip the 2 colors around, this is also the same. So you also have that if you have a 1 input, 2 output red spider, then it copies things that are x basis states, because this red spider is copying anything in the x basis. So notably, a common mistake is that this phase here needs to be either 0 or pi. So you cannot copy if the angle is anything else. So for example, pi over 2 or any other angle that's not exactly 0 or pi. This also holds more generally, so you can do a dot dot dot. And this dot 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 notation is commonly used because you can what the most intuitive notation of what you think this means is that, and what it does mean is exactly that. It's that if you have arbitrary number of outputs, that's 1 or more, say, then this will give you 1 or more of copies. It also works for having exactly 1 output, in which case this is just identity. So this is really convenient as a rule. And I'll take a picture now, so you guys will have the notes afterwards. So Rosine also covered spider fusion, but there's a special case of it that we're about to see. Actually, I'll do. So notably, this is fusing any two red spiders. You specifically need to have at least one wire between the two red spiders to do the fusion. And then you can, as long as you have that condition, you can just fuse the two spiders together such that the total number of legs going outside of these two spiders is the same. So let's say from bottom to top, you've got I1 inputs wires, input number of qubits to the first spider, and I2 number of wires into the second spider. And you've got O1 outputs of the first spider and O1 outputs of the second spider. And it doesn't matter the number of legs in the middle as long as it's at least one. Then the new diagram is going to have I1 plus I2 inputs and O1 plus O2 output wires. And you just add up the phases together. This is pretty easy to check with bracket notation as well, just looking at the definition of the X spiders. Because the way that one X spider is defined. Let's just, yeah, it'll be. I'll do this curly O, so it's not a zero. So the way that the X spider is defined is exactly this X spider, and you've got I inputs and I outputs. And what you're doing when you fuse two spiders is that inputs of one spider to be the outputs of the other spider. So specifically, this spider, these outputs of this bottom spider is connected to these spiders of the input spiders of this top spider. And so then you're matching them up. If when you do this multiplication, if you've got the inner product of plus and plus or minus and minus, then that's just the number one. And if you got the inner product of plus minus or minus plus, then that's the number zero. And those terms that are zero go away. And so what you get, that's why this is correct. And you can verify it quite straightforwardly, but we don't have to do the calculation. So this is a really powerful rule because it's tensor network contraction. So you can think of ZX calculus diagrams as being a quite specific type of tensor network. So instead of having general types of vertices, just using Z and X is enough to describe any qubit quantum circuit, or it doesn't even have to be a circuit. It could be like graph states or other kinds of protocols as well, or measurement-based protocols. This also holds in the other color. And for qubit ZX calculus, any rule that holds in one color, or any rule that holds, if you change all the reds to greens and all the greens to reds, then that same rule also holds. So a special case that Rosine didn't get to last week, or 2 days ago, is that you have addition. Addition of modulo 2, so that's bits, as a special case. So for any bits A and B, adding because after fusion of these three spires, you get the total phase to be A pi plus B pi. But because your phases are always modular 2 pi, that's just A plus B mod 2, or also known as AX or B times pi. So this is quite useful because now we've got basically this thing is the copy box. So if you just consider only bit inputs, that's a basis for all your quantum states, all the computational basis, just all possible states that you can write as bit strings. In this case, just one bit. This is copy. And this one, this also works with the dot dot dots, by the way. So I'm just gonna call this A1 to AN. In that case, this would be the total XOR of I equals 1 to n of A sub I pi. And this is the addition box. Now, this is pretty cool because it gives us a really simple way to think about the certain quantum gate, and it's also the just this one quantum gate is enough to give you all multi-qubit. This one 2-qubit gate is enough to give you all multi-qubit operations. It's the C0 gate. So I'm gonna first claim that the C0 gate looks like this. So this is a claim, and we'll check that it actually does work. And we just can check it by plugging in all the computational basis states. So first, we can just first do the copy, and then you get, oops. This after the copy. Then we can do the add. And we get this, which is A pi on the control of the C0, which is the green one, the left one. And we get A XOR B pi on the right one. So we can see that the C0 gate is why it is also called the C sum gate, because it does addition of the 2 bits that you put into the target. So in fact, we could have done this proof without needing to plug in a B pi at all and to see what the C0 does. So this kind of shows why it is called C sum. And in some generalizations, it's for example in qubits of the C0 gate, it's also called C sum because you copy the control and then you add that to the target. So I can also show the same proof, but now without the bpi, just an open wire. And this is something quite useful with graphical calculus, is you can just have open-ended wires, and it's a more general, being able to do some proofs without needing to know what the input is. And for this lecture, and also usually the convention is that alphabetical letters like A, B, C, these ones are usually for bits, and Greek letters like alpha, beta, gamma, these are usually for angles that's from 0 to 2 pi. That way, that way I won't have to write A or B is either 0 or 1 everywhere. It's just kind of useful.
Please, can I ask a question?
Yeah, go ahead. And I'll keep drawing.
Please, I don't know, like, can you elaborate what exactly is the difference between adding the QSTs and entangling them?
The QST?
Like, entangling the QSTs or adding them, like, how is that different?
Sorry, what is the acronym that QST means?
Like, I mean, the entangling the QSTs, not QST, QSTs. Qubit sticks. Yeah. To entangle qubit sticks and then to add them, like, what's the difference?
Oh, okay. Yes. So the C0 is an entangling gate. So this gate entangles the two inputs if the two inputs were not already entangled. But it depends on what basis the inputs are in. Okay.
So that means we can add two qubits to entangle them, right?
Yeah, so far I've just talked about when the inputs are just ket 0 and ket 1. More generally,
Okay.
we have quantum states, which are superpositions of these ket 0s and ket 1s. And then the C0 gate, how the C0 gate behaves is exactly fixed by what it does on an orthonormal basis. So I'll write that.
Okay.
I'll do something very important. I'll write that I was gonna write that right after this. So stay tuned. So here, without this open wire bpi, instead of bpi, just open wire. Now you can copy this api, and then you can fuse. And that gives you api on the control qubit, which is exactly the state that you plugged in, that you had before the C0 gate. And on the target qubit, whatever your input was, you apply an X gate to it if and only if A was 1. So if A was 0, then this is a rotation of about the x-axis of the Bloch sphere with angle 0. But rotating an angle of 0 is just the same thing as not doing anything, so that's identity. And rotating an angle of pi, if A is 1, just means you're doing an X gate. So this way you do an X gate on the target qubit if and only if the control was the ket 1 state versus the ket 0 state. And this gets into what if your qubit was not in exactly ket 0 or ket 1? In that case, if your input state was alpha, you know what, I'll use a different notation. Let's just use it some scalar. You know what, I'll just use C for complex number. C. So although usually you don't need to use sums in the calculus. In fact, to do this C0 plus C1, this actually is a specific angle of X rotation gate that you could do to get real valued C's, for example. But I'll just write it like this. These are linear, so these sums you can actually also take out of the whole diagram. So it's equal, so you can distribute this sum over the whole diagram, all correct. So if you know that, so that's why how this thing operates on how the C0 gate or any diagram, any quantum process operates on any pure state is exactly the linear combination with those respective coefficients on some orthonormal basis that that state is expressed in. Yeah, we won't need to use the sum so much. It's just, for example, we could have replaced the sum with some operation that gives you that exact superposition. If you wanted to not deal with the sum, but it kind of just shows that it is exactly fixing what this state does if you only know what it does on any orthonormal basis. In fact, when I said any orthonormal basis, so far we've only considered the z basis, the computational basis. But there is a theorem for any matrix, let's just say any diagram even, because every diagram is just some matrix. If there's no inputs but only output wires, then it's a state. And if there's no outputs but only inputs, it's the bra of the ket. So it's a row vector instead of a state would be a column vector. So let's say you've got I inputs and O outputs. So we say that these two diagrams are equal if and only if they interpret to the same matrix. Because every diagram uniquely has one matrix in the computational basis, but has one matrix that is what that diagram implements. So for the C0 gate, this matrix is this one. And one kind of cool thing is that I'll draw this better. There. So this is a theorem. I think it's quite straightforward, so I don't think it has a name other than if two diagrams D and D prime have the same number of inputs and outputs and they are exactly the same matrix, then that's the same thing as saying that for all basis elements, all basis states in some orthonormal basis, that D and D applied to that basis state is equal to D prime applied to that basis state. So left to right is sort of obvious because if D and D prime are the same matrix, no matter what states you plug in on both sides, it's gonna you're gonna have D applied to that state is the same as D prime applied to that same state. Going from right to left, the proof is just exactly writing down your arbitrary single qubit, your arbitrary could be multiple qubit state as a linear combination in this basis, and then just using the linearity, it follows that the right-hand side follows exactly implies and necessarily requires that the left-hand side holds true too. So where I'm getting with this is that we can also see what the CNAT gate does on the X basis. For this, I'm not sure yet if we've covered, if in the past weeks you guys have covered that you can bend the wires of the spiders very freely. So only the total connectivity of the diagram matters. In particular, it's kind of fun to use different colors because it's kind of mystery, like what am I going to draw before it's finished? So in particular, all three of these diagrams are exactly the same matrix. They're all the CNAT gate. And in fact, we could have done some weird squigglies, like as long as it eventually connects to all the connectivity is the same. So as long as the total inputs and the total outputs are preserved, and then inside the diagram, however you want to bend the wires, it's okay. So these are equal, even though this will be something horribly complicated as a matrix or as like, yeah, we wouldn't have yet learned how to write this kind of thing, and you don't have to worry about it. But we can just confidently say that this is true. But in fact, we'll shortly know what this kind of squiggles means. Like, what does it mean to not just have a straight edge, like inputs and outputs? So kind of already we're breaking down the CNAT gate into, we can also have information. In fact, it's exactly one qubit of information in the middle of the CNAT gate. So you can think of it as it's a virtual qubit here. And this virtual qubit, because it's a virtual qubit, it's maximally entangling. So it's exactly one qubit of information that can go between. So it's just a unitary single qubit wire that connects the two sides. So in this picture, now we'll look at this thing. Now let's plug in to this thing, and with the target being an X basis state. Sorry, I have messed up a bit here. The colors should be green on the left and red on the right. There we go. First, we can copy. Oops. And then we do one more fusion. And so this is the exact same proof as down here, except now we've just flipped the colors. So now instead of plugging a Z basis state, either ket0 or ket1 into the control of the CNAT, now we've plugged in an X basis state to the target of the CNAT. And so this, we can see that if the target is an X basis state, it's either ket plus or ket minus, then if the target of the CNAT gate is ket plus, then there will be a Z gate on the control of the CNAT. Meanwhile, if the target gate is ket minus, then there'll be a C naught. I'm sorry, I'll go back a bit. If there's two cases. B equals 0 is the ket plus state. And then there's identity on the control. So I'll write that. So these are the two possible cases. Either nothing happens to the control or Z gate happens to the control wire. So it's kind of interesting because you can see that because you're viewing the C naught, not only what it does in the computational basis, but also what it does in the other basis, the X basis, then that tells you about how doing things on the target affects things on the control wires. And in fact, this more general principle is quite common with the idea of quantum oracles. So this is just a 2-qubit input 2 output case. But you're plugging in a superposition, in this case, an equal superposition to the state, to the target. And classically, if you're just restricted to just zeros and ones, you can't express this kind of superposition state input. So you're not able to, like, say, plug in things. This is a quantum state, and this works because it's a quantum state. So for oracles, they're usually of this kind of form. This is not covered in the course usually, but I think it's just too fun not to. Plus, it gives some intuition. So more generally, you could do this kind of function for an oracle, which is that you copy your inputs. In fact, you could copy multiple inputs. I'll actually redraw it. So here this f is a classical function. So it just takes in some bits and then does something with it. So it takes in and f is some classical function that takes in m bits and gives you 1 bit output. For example, f could be like addition modulo 2 of all of them, or like multiply with some secret vector, some secret bit string.
Hello. Yeah.
Yes.
Yeah. Please, can we have your camera facing the board well? Yeah. Good. All right. Thank you.
Thanks for asking. Yeah. So this is kind of a fun fact, but it's also extremely useful, I think, for thinking about oracles. So if you have m inputs here and m outputs here, output number of qubits, this thing is going to be equal to the typical use of f, your typical oracle for some classical function f. Some notation you'll see is that this is some bit string x, and it outputs that same bit string x, and this is some bit y, and it'll give you y, x, or, I'll write it bigger, y, x, or f of x, with the vector x there, where x is your input to f, the function f, some bit string. And these bit strings are just these computational basis states. So Ribzine showed these bit strings, like for example, if X is just like, if this was your state, then this would be the bit string, let's say left to right, just 0, 1, 0. Yeah. Because it's ket 0, ket 1, ket 0. So this thing is always unitary because what it does is copy the computational basis state inputs and then does some function and then adds it XOR to these whatever the input qubit of the target input qubit was. So sometimes you'll do an X gate, sometimes you won't, basically. And whether or not you do, this thing is always unitary, even though F itself is not unitary. And typically with quantum algorithms, you'll have a trick is that you can plug in something green here. And something green is going to be not expressible with just bits because it's a superposition of, say, all the possibilities. If you plug in something, for example, green I here, then this is ket 0 minus ket 1. And then you can, like, for example, look at the minus sign when you measure, and that could tell you something about F. Okay, there we go. So anyway. There we go. So now it's picture time, and feel free to ask any questions before I'll move on to as well as I'll erase the board. The main thing to cover for us today is the CNAT gate, so I think we were doing really good on time.
Hello, Leah. Yeah, I think I have a question in the chat. There's a question on the chat there.
Yeah, so let's see. The question on the chat is asking if I flipped the qubits. Let's see. This was a while back, so I'm not sure which part of the can I ask
Yes,
where?
from the C note, you know, you made mention that the C note gate. So C note, and then exactly that place you have there. So you saw it. So you said it's the same. It looks the same or similar as the one there. So I was asking if maybe the qubits have been flipped.
Yeah. Give me a sec. So far, all of these I've always drawn the control to be the left and then the target to be the right. So
Okay.
So I'll just draw this here.
So from there, the control is at where the left and the target is.
Yeah, in circuit notation, this would be this thing.
Okay.
All the left and the target on the right. So the control is always green because green is what copies the computational basis state, the Z basis state. And the target is always red for CNOT gate because that copies the X basis.
Okay. So the green and the red, is it like the X and Y spider? Or
Yeah.
Z and X spider?
Yeah, it's exactly the three-legged green spider and the three-legged red spider, where one leg of each is connected to each other.
Okay.
like this, like these ones here. So I'll do some erasing. And next I'll translate all of the gates and single qubit and multi-qubit states, gates, and measurements that you need for a universal gate set. From circuit notation and ZX calculus notation and bracket, if it makes sense. So I already wrote the single qubit states. I won't write that again, I guess. Okay. And Rosine showed the color change rule last week, which is which is just a square. A Hadamard gate is just a single qubit gate that is a square with one input and one output. In fact, because only connectivity matters, you don't need to worry about if this is input or output. So specifically, we can see a different example. The CZ gate. I'll first draw the one way that you could draw a CZ gate is well, it's just equal to a CX gate, but you put Hadamards on both sides of the target. This is the CZ gate is equal to a C0 gate with Hadamards on both sides. And we can color change using the color change rule that Rosine mentioned last week. In addition to color change, we also recall that 2 Hadamards in a row is equal to identity. So once we color change, we have that this is exactly the ZX calculus diagram for the CZ gate. Because you can color change this red to become green, and then you get Hadamard, 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 but there's already was an additional Hadamard here and here to start with. So those 2 Hadamards will become identity. And these 2 would become the one from changing color plus the one you had here originally will also go away to be identity. And then when you're left with only one total Hadamard, which is this one. Does that are you guys good with the color change, or should I write it more explicitly?
Hello.
Yep. Oh yes, there we go.
Okay. I think you've done it. I wanted to put a camera
So I will recap the color change. It's a quite a bit to take in with lots of rules. But if over time you could get the hang of it, but it's memorizing some rules at first. But it turns out you don't need so many rules. So no matter what the phase of this spider was, if you put a Hadamard gate on to all legs of the other color spider, that they're equal. This also means that you can push Hadamards through. So let's say you wanted to push this one through. Then you could first apply the color change. And then you can apply this to Hadamards as the identity. So usually if this right-hand side diagram is equal to the bottom, just like you would do with equations, you can put the equal sign here. So this concept of pushing through things is quite convenient because you can just push any Hadamard through any spider, and all it's going to do is change that color and give you a new Hadamard on all the edges, which had no Hadamard before. Doing that here on the C0 gate with conjugated by 2 Hadamards on the target, you could push, for example, this one through, and that will give you no more Hadamard here. You'll change the color of this, and you get a Hadamard here, and then one more Hadamard here. Then these 2 Hadamards will cancel and become identity. So in the end, you just have one total Hadamard, which is over here. Then we can have a theorem. Oops. So a universal gate set is, I'll just put it here. So this following is a universal gate set. So all single qubit X rotations, all and Z rotations of any angles, and C0 gates. So this means that if you have So I'll write this in, so in CX, and we drew it before. And if you have Z basis single qubit states, initialization and measurement, then you can non-deterministically implement any matrix. We won't have to worry about determinism so far, because actually it's probably better to just say that. So you can implement, this is equivalent to saying that you can implement any unitary matrix of size 2 to the n by 2 to the n, or some natural number n, deterministically in this gate set. And thus do any qubit computation. Thus represent, let's say, thus decompose any qubit computation into these operations. So sorry, it's a bit more technical definition, but so basically this definition is about universal quantum computation. If you don't have, although you only need 3 gates in this case, in fact, some gate sets you only need 2, but you can exactly write any unitary matrix that of size that is like some size, some power of 2 by some power of 2. So any qubit computation you can always write in just these gates. If you just have access to these gates plus single qubit states in the Z basis of just ket 0, ket 1, and just single qubit computational basis measurements. So just bra 0 and bra 1, those are the observed possible measurement outcomes. I'll also note that the Hadamard gate you can also write into some combination of Z and X and rotations. So in fact, any single qubit all right, for any single qubit unitary, so any single qubit gate U exists alpha 1, beta 1, gamma 1, alpha 2, beta 2, gamma 2, such that I'll draw the colors right after this. And I've lost my green marker somewhere. Oh, here. There we go. Yeah. Such that this is true. And this because one way to think about this is that any unitary that's a single qubit unitary is just some rotation of the Bloch sphere. So any state on the Bloch sphere gets rotated. If you do that rotation, then that point where it becomes after that rotation of the sphere is going to be exactly where you end up. And any rotation of the Bloch sphere, so this like real 3D space, is also equal to doing, if you first do some rotation about an x-axis and then the z-axis and then the x-axis like this. That's the same thing. Oh, sorry. Like this. That's the same thing as doing a z rotation and then an x rotation and then a z rotation for some other angles. And you can do some trick to figure out which angles correspond to which ones. So for example, for the Hadamard gate, you could just have all three of them be pi/2 up to some global phase. Okay, so there's some angle. Oftentimes the global phase doesn't matter because you can't physically observe this kind of global phase. And I think that kind of wraps up the lesson today in terms of like content-wise, but I'm very happy to stick around for some questions. And I will also send all the pictures to you. Maybe I can even do that. Probably, let's see. Sending it in Zoom is probably not so useful. So I'll send it to Katarina and I think they'll be shared with you.
Okay. Please, is there any question? So they will have access to the video. So we'll upload the video onto the platforms for them to view. So if there's no
Please, I have a
question.
question.
Okay.
Please, I wanted to ask, the universal
Go
gate
ahead.
said that I'm talking, the universal gate says that she just used here. Is it the only universal gate set, or maybe there are other gate sets that can be expressed?
Yeah. So there's many different universal gate sets. Some are exactly universal and some are approximately universal. In practice, approximately universal just means that you can't exactly implement any matrix, but you can implement any matrix up to any unitary matrix up to a little bit of error. And as you use more gates, so you've got more gate count in your circuit, you can get that error to be smaller and smaller and smaller until it's exponentially small. So it's kind of negligible error. So we will some examples are the Clifford plus T gate set, which is the CNOT gate plus the Hadamard gate plus any angles that are multiples of pi/4, which includes the Hadamard gate. So if, for example, if you restrict alphas to be integer multiples of pi/4, that's not going to be able to give you any phases that are not multiples of pi/4 exactly, but you're still able to approximate any quantum computation on qubits up to arbitrary low error, just by making your circuit longer. So that's about approximate universality. As for non-universality, which kind of gate sets don't have universal are not universal? Let's say that we got rid of the CNOT gate. Then this is certainly not a universal gate set because there's absolutely nothing here that gives you any entanglement. So you need at least one entangling gate to be able to entangle qubits together. So, but in fact, just one is enough. For example, the CNOT to get universal quantum computation. So you need at least one. And also, if you only had, like say, only had Z rotations and just CNOT gate, this doesn't give you any ability to rotate about the x-axis of the Bloch sphere. So there's nothing you can do to change relative to the x-axis of any of the qubits. So this is also not a universal gate set.
Okay. Okay, so that means that though the three comes together to form the universal gate set, but we can express them, we can use two to express the whole operation, like decompose the operations, right?
Yeah, that's correct. And so in fact, this corresponds to the exact universality result for ZX calculus, which is that because this is a universal gate set, then any qubit quantum computation you can write as a circuit made out of just ket 0, ket 1 states, followed by some circuit that's just these gates, followed by measurements in the computational basis. And therefore, any qubit quantum computation you can always write as a ZX calculus diagram of just spiders.
When you talk about the color change here, let's say you want to convert it from red spider to green spider. Is it all the time we have to apply it to the same side, or maybe sometimes you have to convert maybe red to green, you have to apply it to the reverse, the Hadamard gate to the reverse side, maybe reverse way?
Yeah, so for example, if you want to fuse two spiders and they are different color, but you've got a Hadamard in between, then you want to fuse them. You want a first color change, and then you can do a fusion. So one example is the Bell state circuit. I'm kind of jumping ahead a little bit, but you'll have to see this sooner or later. In fact, you will see this very soon. But so this is your usual Bell state circuit. Like that. And in ZX calculus notation, just translating everything one at a time. So this ket 0 is this ket 0, this Hadamard is this square, and this CNOT K is like this. Then you can do the color change first. And now this red with this Hadamard and all of its legs, it just has one leg, is now green. Like this. Then you can do fusion. And you get this. But this diagram has 0 inputs and 2 outputs. So this is an internal edge. In any case, this is a green spider with 2 legs, which just means that it has it's a Z rotation of angle 0, so it's identity. And same with this is an X rotation of angle 0. So you can just take away both of them, and you exactly get this. So by the way, this straight edge, it could have also been like this, or like this. It's not important because this rule that you can take away this spider doesn't matter which direction the legs are. Yeah, like that. And this looks pretty funny as a diagram, but it's just exactly a 180-degree bent wire. So for example, the identity wire would send ket 0 in the input, to ket1, sorry, ket0 in the input to ket0 in the output, and then ket1 to 1, and any whatever input state to any whatever output state says that they're the same. And this thing says that if you put in ket0 here or bra0, then you exactly get ket0 here. And if you also put in ket1 here, you get ket1 here, or bra1, I guess, bra1, yeah. So you'll see a bit more about why this is just exactly a 180-degree wire in the coming weeks. So I probably shouldn't spoil so much. But in any case, this is an example where you color change, so you have a Hadamard applying to a Z basis state, and it changes the basis from Z basis to X basis. And so now it becomes green, and this lets you do a fusion that you couldn't do before.
Okay, thank you.
Hello, Leah.
Hello.
Yeah. Do you have any recommended book for us on this? If you could share with us any book on this ZX calculus.
When you say notebook, do you mean today's photos or lecture notes or
Textbook.
textbook? Oh, okay. Yeah, there is a course textbook. There's the one for the high school students, but that one doesn't have bracket notation and matrices and circuit notation because those were for, well, those they haven't learned those yet. Like, for example, most high school students in the UK has not gotten exposure to matrices and how to multiply and tensor product them. So, but I also have a different tutorial that's about the translation. So yes, I can send all of those. I'll just send them to Katarina along with these photos, and I'll make a note to myself here to do that. Well, for more questions, feel free to, Henry, can I ask what's the best way for them to send questions?
Okay, so the participants can type the questions, and also if you have any question, you can just unmute and then. But we would share the video with them on YouTube, so we can go back and access the video. And also the document, I think you send it to Catalina, so we'll pick it from there and send it to them to their class, virtual class.
Mr. Henry.
Yeah.
Please, if I understand Miss Lia very well, she's asking if we could reach her later in case we have some questions.
Okay.
Please, Miss Lia.
Okay.
Yeah.
Okay. Okay.
Yeah. So I should mention, so Boldy, Razine, and I, who are three of the tutors for 3 of the weeks, we are also helping like work with y'all on whoever's doing the final projects. So it's kind of like a team guided research project. It should be very fun. I'm very excited for it. So that we'll have our contact info shared towards later on in the course, maybe the last third of the course. And you'll get to explore different applications, maybe whichever you're more interested in within quantum computing, and take a look at it. So that would be a good time to ask questions as well.
Okay.
Yeah,
I didn't catch that because of I didn't catch everything. My network is a little bit unstable.
And also, don't hesitate to ask any of the tutors in future weeks if you have any questions, because they'll be happy to answer.
Okay. Okay. So I'll start that with Dr. Martin, then we'll get back to you on that. Okay.
Yeah. Well, thank you everyone for joining the lecture. I hope you learned some of it, and it was fun. and look forward to the final projects.
Okay. Thank you very much for honoring our invitation, Leah. So we'll keep in touch, and I will let you know of any progress. So, so for the participants, we thank you all for coming for today's session. I think we have another session next week. We have some sessions next week. We will let you know if we have any other talk or to do in the week. I will do well to put this video, upload this video on YouTube so you can easily access it. Thank you very much for coming.
Thank you, and enjoy the rest of the course.
Thank you, sir. Thank you very much.
Have a good day.
And thank you.
Have a nice day.